Hello students, welcome to another lecture number 3 of electric charge and fields. So before you watch this video, please watch the first two lectures. Links are given in the description box for better understanding. And topics we are going to discuss here in this video are electric dipole moment, electric field at a point on axial line of electric dipole, and field at a point on equatorial line of electric dipole. So before we start, please like, share and subscribe the channel. Okay, so what do you mean by electric dipole? So electric dipole is nothing but a pair of equal and opposite charges separated by a very small distance. Suppose we have two charges. One is negative charge, another is positive charge. It is a pair of charge, and if they are separated by a very small distance, and that is suppose twice a, then this is called a dipole. Okay, this is its charge on this end is suppose negative q, and this is on positive, this is positive q. Okay, so this is an electric dipole. Okay, so now what do you mean by the electric dipole moment? So let me scroll down page. Suppose here you see this is the negative charge minus q here, and this is the positive charge and charge on this positive q, and the distance between these two charges be suppose twice a, then the dipole moment is given by is represented by small p, and it's a vector quantity. It's given by q on its charge on its end in its pole. Okay, charge on its pole, that is suppose q here, and the separation between them, that is twice a. So this is a vector quantity, dipole moment. Okay, product of these two, product of this charge on its pole and the length separation between the charges is the dipole moment, and its direction of this dipole moment will be from negative to positive. So if this is the dipole here, you can see if this is the dipole, then direction will be from negative to positive. SI unit of dipole moment, remember the SI unit of dipole moment is coulomb meter. Okay, and the dimensional formula that is m to the power 0 L T A. So this is the dimensional formula. So now we are going to discuss about electric field at a point on axial line of a electric dipole. So our next topic is electric field at a point on the axial line of a dipole. Suppose we have a dipole. Let us suppose we have a dipole. So this is the dipole consisting q positive charge and q negative charge, and separated by a distance r. Sorry, not r. It's twice a. These two are separated by a small distance twice a, and the center of this dipole be suppose O. The center of the dipole is suppose O, right? Suppose we have a point on the axial line, the line passing through these two charges be suppose point P, and this is the point P. Here is the point P, suppose. So we are to find the electric field due to positive q charge, due to discharge at the point P, So that should be directed away from the positive charge, because we know for a positive charge, the electric field lines comes radially outward, so that is the direction of electric field. So here the electric field due to the positive charge, let me write it E plus, let me represent it by E plus, right? Let me use the symbol E plus. This is to represent electric field at P, electric field at P due to this Q positive charge, due to this Q positive charge, right? So, and let us represent the electric field due to Q negative charge, due to Q negative charge at point P. So that means that should be going into the Q negative charge. So here is the Q, suppose this is the negative charge, then electric field due to this negative charge is radially inward. So field due to negative charge is radially inward direction. So let me represent this field at point P, at point P due to the Q negative charge. This is the direction of that field in yellow color. So let me represent it by E negative, E minus. Okay. So now let us consider that distance between this point P and the center O. Distance between this point P and the center O, we suppose R. Let me consider this distance is R. So now here you see the distance between these two positive charges we have considered twice a, and center is O, right? O is the center, O is the center. So that's why distance from the center to its charge should be A, right? Distance between the O and Q positive and that between the O and Q negative, in each case that should be A, right? So in that case, here you see, if you observe these distances, distance from Q positive to O is A, and distance from P to O is R, right? So that's why distance between Q positive charge and the point P, distance between P and Q positive charge, that distance should be R minus A, right? That should be R minus A, R minus A. And as you can observe here that distance from O to Q negative charge, this is A, and distance from P to this P point to Q positive charge, this distance, right? This distance is R. So distance from P to Q negative charge, distance from P to Q negative charge, that means this distance. So let me show you this distance from P to Q negative charge, that should be R plus A, right? That should be R plus A. So R plus A is the distance between P and Q negative charge. So hope you have understood. And we know, suppose this is the electric field, suppose this is a charge, suppose Q, and here we need to find the electric field at this point, suppose, and which is at a distance of R. Then electric field at this point is given by E is equal to KQ by R square, right? R is the distance between the charge and that point. So in this case, if you find the electric field due to, so electric field due to Q positive charge at P, then as distance between P, as the distance between P point and the Q positive charge, as we have got from the diagram, R minus A, right? R minus A. Then if you apply this formula, here you see in yellow box, if you apply this formula, the R square, this R square should be replaced by R minus A whole square, right? R minus A whole square. Then that should be, that will be, so let me represent it E positive, E positive that represent the electric field at P due to Q positive is suppose E plus, and that is equal to KQ by R square. Means here instead of R we have to take R minus A whole square, because distance between the P point, distance between the P point and Q positive charge is R minus A, right, is R minus A. So now let me scroll down the page a little bit. Electric field at P due to negative Q charge. So here you see, if you check the diagram here, so if you observe the diagram here, you see, let me write it, let me clean this part. So then you can find that distance between this point P, here you can see distance between this point P and the Q negative charge, distance between this point P and Q negative charge. So this is the point, suppose P, and this is negative Q charge, suppose point P, negative Q charge, this is negative Q charge. So, and this is the center O. So distance between the center O and Q negative is A, small a, and the distance between the center and the P, point P and O, that distance is, we have considered that it is R, right? So therefore distance between this positive Q negative and point P, this distance between these two is R plus A. In that case, our electric field due to Q negative charge at the point P, is given by E minus KQ by this. So electric field at P due to Q negative charge at point P, at this point P due to Q negative charge is E negative KQ by R plus A whole square. So here now, as you can see, this is the point P, suppose, and this is Q positive charge, and this is negative charge. Here is the negative Q negative charge. So here Q positive charge is closer to this point P compared to Q negative charge. So electric field due to Q positive charge at P, that is E plus, that will be greater than that of due to Q negative, that electric field due to Q negative at this point P in opposite direction, that is E minus. Okay, this E positive is greater than E negative because Q positive charge is close to P compared to negative Q charge, right? So that's why E positive is greater. So, and you see these two fields, electric field E positive and E negative, are in opposite direction. They are in opposite direction. So therefore net electric field at this point P, net electric field at this point P, will be given by net electric field at point P is E is equal to E positive minus E negative. So now let us put these two values, E positive and E negative, let us put these two here. Let us put this two here. So if you do so, let me write here, then what you will get, E is equal to KQ by R minus A whole square minus kq by r plus a whole square. Okay, you will get this. So now let us take kq common. So here you can write, taking kq common, 1 by r minus a whole square minus 1 by r plus a whole square. So then what you will get if you simplify, r minus a into r plus a whole square, then r plus a whole square minus r minus a whole square. So you will get this. Now if you simplify this, then you will get E is equal to k q 4 r a by r minus a r square minus a square whole square. That's what you will get, right? So now here you see, let me scroll down the page. 4 r is very greater than a. If r is very greater than a, then this a square can be neglected. Then we can write E is equal to k q 4 r a by r square minus a square. A square is neglected, so we will get r to the power 4 here, r to the power 4. So this r cancels, r cube is obtained. So now here E will be equal to this k, and we can write 2 q into twice a, right? We can write this part as 2 into q into twice a. So we have a purpose, that is what dipole moment P is equal to q into twice a, right? So you can replace this part by this P. You can replace this one by P, dipole moment P. Okay, so then our expression becomes equal to k 2p by r cube. Okay, and this is scalar form. So what will be the vector form? So E vector, that's gonna be equal to k twice. So dipole moment is a vector quantity, so twice p and r cube. Here we will get r cube, and this is the vector form. And from these two expressions we can say clearly that the electric field E is inversely proportional to r cube, right? So these are the this is the vector form of the required expressions. So here one thing is clear, E is inversely proportional to r cube. That's what we get. Now let us find the electric field at a point P, suppose, which is at the equatorial line of a dipole. This is suppose minus q. Suppose minus q charge of a dipole, and here is the plus q charge of a dipole, and this is the center O. Then the line perpendicular bisector to this line joining these two charges, that is the equatorial line, and here we have a point P. So now we are going to find the electric field at this point. Let me show you how. So now our next topic is electric field at a point on the equatorial line of electric dipole. So here we have an electric dipole, here you can see, and it consists two charges, equal and opposite charges. This is suppose negative q charge, and here it is positive q. So let me take this one positive and this one as negative q charge, and here is the center of this dipole, suppose, and these two charges are separated by a small distance twice a, and so we can say OA is also equal to A, OB is also equal to A, right? And there is a point at a distance r from this center, okay, on the equatorial line, that is suppose P. Okay, this distance is r. So now we know the direction of electric field due to positive charge is radially outward. So direction electric field at this point P due to this q positive charge should be directed towards this direction, radially outward, and due to electric field due to this q negative charge should be directed towards q negative in this direction. So here is the field, direction of field due to q positive charge, and direction of electric field here E minus. This is E minus. E minus is due to q negative charge directed towards q negative, right? This is the direction, right, of q negative, and this is the direction field due to q positive, right? We have considered that way. Now here we have OP is equal to R, OA and OB is equal to A, and using Pythagoras theorem you can write PB is equal to PA is equal to root over R square plus A square. If we use Pythagoras theorem you will get that. So now let us assume that angle between so here E positive is field due to positive q charge, and E minus is suppose field due to negative q charge. Okay, so angle between these two vectors, suppose twice theta. So we have assumed twice theta. Now let us resolve into two components. In two components, its vector. Let us resolve its vector into two components. So here you see. So first, if you resolve E positive, E plus into two components, that's how you will get. So as you can see, this angle is twice theta. So therefore, this angle will be theta, and this angle will be also theta, right? So hope you have understood. This is theta and this is also theta, that's why 2 theta. So now let me clear this. So here you see, so as this angle is theta, so this component should be, let me use another ink, this component should be E positive sine theta, and this should be E positive cos theta, right? And again, if you resolve E negative into two components, so you should get again one component along this direction, another component in this direction. Here you can see, right? So this component is E negative cos theta, because this angle is also theta, and this component here you can see this component is E negative sine theta, right? So you will get that. Now these two components, positive E positive sine theta and E negative sine theta, will be oppositely directed because of opposite surge, and as the magnitude of surge equal in both cases but opposite in nature, so that's why these two vectors are directed in opposite direction, so that's why they will cancel out each other. Okay, so we can say E positive sine theta and E negative sine theta, these two will cancel out each other. Okay, so these two will cancel out each other, will cancel each other, right? So now let me scroll down the page. So here you can see each other, because let me write, because they are equal and opposite in direction, right? So that's why they will cancel each other. So our resultant field will be due to these two components, E minus cos theta and E plus cos theta, right? So now what we're going to do here, you can see that magnitude of an electric field due to a charge q is given by electric field magnitude of electric field at any point due to a charge is given by, we know that 1 by 4 pi epsilon naught q by r square. R square is the distance between the charge and the point where you are going to find the electric field. But here you can see in the diagram, so the distance between q positive charge, so the distance between this q positive charge and the point P is root over r square plus a square. So that's why according to this formula, if you use this formula, we will get, let me clean this first, you will get that electric field at P due to positive q should be equal to, so let me write here E positive, that should be equal to q by so you can write 1 by 4 pi epsilon naught, q positive means q, you can write, and instead of r square there will be root over r square plus a square whole square, right? So on squaring this root will be gone, so that's why you can write, let me scroll down the page, so you can write E positive 1 by pi epsilon naught r square plus a square. So similarly, as you can see here, now you can see charge on each pole is q, equal in magnitude but opposite in nature. So that's why this field at P due to both charges must be equal. That means E negative and E positive must be equal. Okay, so electric field due to minus q is also equal, right? That's what we will get. So now you see from the, if you see the resultant electric field, if you see the diagram, so let me clear this one first. If you see the diagram here, when we have resolved the electric field into two components, the cos components of both electric field E negative and E positive are directed in the same direction. Okay, so resultant will be sum of these two, the resultant field will be sum of these two, E minus cos theta and E plus cos theta, right? So therefore we can write resultant electric field that must be equal to, we can say E, that must be equal to 2 E positive, you can write either E positive or E negative because both are equal in magnitude cos theta. So this is equation number 1, right? Sorry, let me give it equation number 2, and this is equation number 1. Okay, now if you use 2 in 1, then what you will get, right? That if you use equation number 1 in 2, that means if you use this value of E positive and E negative, okay, E minus and E plus, these two here, then what you will get, let us put here. So then you will get the resultant field E is equal to 2 by 4 pi epsilon naught q by r square plus a square. That's what you will get, right? So one more important thing is what you will get, so this cos theta is here, cos theta. Okay, so what we have done, we have replaced this E plus by this value of E plus. Okay, so hope you have understood this. So what we have done here, we have using 1 in 2. Okay, using 1 in 2. Now you see here from this diagram, if you take this triangle, so let's move back to the diagram. If you take this triangle POB from this triangle, so this side is A and this is R, so we have considered here, you see, if this angle is theta, then this must be also theta and this angle must be also theta, right? So here you see, so let me draw the diagram simply again. So this was the dipole here, this is A, B, and this is negative Q, and this is positive Q. So here is the point P, this is the center of the dipole O. So here you can see this is the field, electric field in this direction and in this direction. So as you have taken this is this angle is twice theta, so that's why this component, cos component of these two fields, E plus cos theta and E minus cos theta, will divide this angle into two equal angles theta. So right, so in that case here you say this component is parallel to this side, that's why if this angle is theta, then this must be also theta, right? If this angle is theta. Now see this triangle. From this triangle, here you can see, let us take this triangle. So here it is R square plus A square, and this is R, and this length is A, right? So from here, so you will get cos theta. Cos theta is equal to, from triangle POB, this point is B, we have taken, this is O, right? This point is P. So from triangle POB, so that is base by hypotenuse, base is A, cos theta is equal to base is here A, by hypotenuse is root over A square plus, root over R square plus A square. That is the value of cos theta. So now let us use this value of cos theta here in this equation. This is equation number suppose 3. So now this is suppose 4, using 4 in 3, then what you will get, then you will get the resultant electric field E is equal to 2 by 4 pi epsilon naught Q by R square plus A square into A by root over R square plus A square. That's what you will get, right? So now you see, if you simplify, so now it is equal to 1 by 4 pi epsilon naught Q into twice A by, if you multiply these two, then what you will get. So here R square plus A square whole to the power 1 you can consider, and root over R square plus A square, that means R square plus A square to the power half, right? So if you multiply these two, then you will get R square plus A square whole to the power 3 by 2, whole to the power 3 by 2. That's what you will get, right? And we know magnitude of dipole moment P is given by Q into twice A, right? Q into twice A. So that's why this E is equal to 1 by 4 pi epsilon naught P is equal to, these terms become P, okay, by R square plus A square whole to the power 3 by 2, since you can write magnitude of dipole moment P is equal to Q into twice A, right? So you can write this, okay? So that is what we have got, electric field at a point P on the equatorial line of an electric dipole. Okay, so this is scalar form. So this is scalar form. So what will be in vector form? Now you see, we know, let's move on to the diagram. Let's move. So this is q negative charge and this is q positive charge, and the dipole moment, direction of dipole moment from negative charge to positive charge, is directed towards negative to positive. This is the direction of dipole moment. Okay, and here you see the resultant electric field. This is the direction of resultant electric field at point P. So this is the dipole moment, direction of dipole moment, right? So that's why here you can see both are opposite in direction. So electric field, resultant electric field, and the dipole moment, they are opposite in direction, right? So since direction of P and field are, these two are opposite in direction, so if you want to write in vector form, then you have to write E vector is equal to 1 by 4 pi epsilon naught this dipole moment vector. Here you have to put minus P, right, because of opposite direction, r square plus a square whole to the power 3 by 2. So this is vector form of the same expression that we have obtained here. Okay, so this is the what, electric field at a point P on equatorial line of an electric dipole. So this is vector form. So hope you have understood this. So thank you for watching. So see you in the next video. If you have understood, please share the video with your friends, and if you are new to my channel, please subscribe the channel, hit the thumbs up button and bell icon as well.